Today we will discuss about electrical resistivity of certain materials. Then we will discuss about temperature dependence of resistivity, and then about electrical energy and electrical power. First of all, resistivity of certain materials. Certain materials. See, good conductors have small values of resistivity. Good conductors like copper, iron, silver, iron, gold, etc. So they are all good conductors or metals. So for good conductors, this is of the order of this much to say some ohm meter. So 10 power minus 8 ohm meter to 10 power minus 6 ohm meter. In the case of insulators like rubber, plastic, porcelain, mica, etc. So they have on the order of 10 power 14 ohm meter. So which is nearly 10 power 18 times to that of good conductors. So in between these two types of good conductors and insulators, there are semiconductors whose value will be in between these two. Now, such insulators are used, or bad conductors are used for making standard resistors of different values. Now, there are two types of resistors. Wired resistors are one type, and resistors made up of carbon are another type. So, in wired resistors, so you can make standard resistors with the help of resistors having standard resistance per unit length. So, wires such as nichrome alloy, nichrome, manganese, and constant. So, generally, this manganese and constant are used for making standard wired resistors. Nichrome is an alloy of nickel, chromium and iron. So which is used for making heating elements because it has a large distance, and even when it is red hot, it will not get oxidized. Therefore, it is used for making heating elements. So the manganese and constant, these two are also alloys. Manganese is made of manganese, nickel and copper. Constant is nickel and copper alloy. So they are also alloys, and they have standard resistance because with the changing temperature, the resistance values or resistivity values doesn't change much. So therefore, they are used for making standard resistors. So the wired resistors here I will show you. So for example, this is these are bobbins are there over which wires of certain length are wound. So this one has small number of windings and its resistance is 1 ohm, whereas these two have 2 ohms and this has 5 ohms. This has 10 ohms resistance. And when you come to this, here this bobbin is having several windings. It has 50 ohms resistance, and this one also, that is 20, this is 50, and this pair has 100 ohm resistance because two 50s are joined in series. So depending upon the windings, you can see black colored windings. Here you can see it as white. So depending upon that number, we can say that it has more length than this, than this, than this. So this has 10 ohm resistance. That wire of that much length as a standard value. So these are made up of this constant current or magnetic wires, so which have standard distance per unit. Now you can use these wire resistors to prepare resistors of values having an order of ohms only, that is from a fraction of ohm to say 100 ohms. And if you want higher resistors, they are made up of carbon. So carbon resistors have large values, and they can be prepared easily, and they are smaller in size. So because of these qualities, carbon resistors are used widely in electronic circuits. I will show you the carbon resistor, and you observe that there are colored rings on them. Since the sizes are very, very small, the values can be identified by with the help of the rings printed on the carbon resistors. So here you can see. So in this you can see that here is a resistor. Here is a resistor, you see. So it has a brown ring followed by a dark green ring. Then you have a red ring. Then you have gold colored ring. So here also there is another resistor. So brown, black, red and gold. So that colors also you can see on the next small carbon resistor. So there is a resistor similar to this one there also with colored rings printed on it. Okay. Now how to identify or how to calculate how to find out the value of the resistance on a carbon resistor. So that we call it as color code. So we follow a color code. The color, then the numerical digit, corresponding numerical digit. Then we have a decimal multiplier. Then you have tolerance. So you can remember this with the help of a simple sentence like this: Roy, Great Britain, very great why. Then you will get gold color, silver color and no color. Okay. So this is gold, this is silver, this is no color. The corresponding digits are, this is black. Black, first one, take it as 0. This is brown, take it as 1. And this is red. And red, orange, yellow, green, blue, violet, grey, white. So here 1, 2, 3, 4, 5, 6, 7, 8. This is 9. So here they don't have any digits here, but decimal multiplier. This is 10 power 0, which is equal to 1. This is 10 power 1, 10 power 2 this color, 10 power 3 and so on. And for gold, it is 10 power minus 1. For silver, 10 power minus 2. And no color has nothing, decimal multiplier. The tolerance is for gold 5%, for silver 10%, for no color 20%. For no color 20%. 20% tolerance. The meaning of tolerance means error plus or minus. That for the given in the given value, there is an error of either plus 5% or minus 5% or plus 10% or minus 10%, like that. So it is plus or minus 5, 10 or 20%. That shows the error in the value. Now the first two rings. So you have seen that the rings on the resistor are like this. Suppose you have this something like, so if you see the shape, it is somewhat like this with the two leads. Now this is the first ring, this is the second ring, this is the third ring, and here is the fourth ring. So what, for example, if this is red and this is red and this is also red, and say finally you have say gold or silver. Suppose gold. So what is the resistance value of such resistor? So you know the red indicates 2. So 2 triple R into 10 power 2. And plus or minus gold indicates an error of 5%. Okay. So that is how we calculate the error in the measurement of resistance using color code. So here okay. Similarly, so this is equal to 2200 plus or minus 5%. So that is the resistance value. So many ohms with an error of 5%. So I can write like this. So 2200 ohms with an error of plus or minus 5%. Suppose if the ring is silver. Suppose it is silver. So silver has a tolerance of 10%. Then you have to put 10 like this. Okay. So with the help of this color code, you can identify the resistance value of the given resistors. Such resistors are widely used in electronic circuits. That's about resistivity. Then we talk about temperature dependence of resistivity. So how temperature affects this value? Temperature dependence. So dependence of resistivity. Okay. It was found that the relation between resistivity at a given temperature is given by resistivity at 0 degree C with this 1 plus alpha T minus T naught. So, if the resistivity of the material at T naught temperature is rho naught, then at a temperature of T, the resistivity is rho T. So, in that way, the relation was found between the resistivity and temperature. Here, alpha is a constant. Alpha is a constant which is called and it is called as temperature quotient of resistivity. Temperature quotient of resistivity. So it has the unit of per Kelvin or per degree C, because that is reciprocal of temperature. The unit of alpha is reciprocal of temperature. So in general, you can define the alpha quotient of temperature quotient of resistivity like this. So rho T minus rho naught by rho naught into delta T. So, what is the fractional change in resistivity per unit rise in temperature for unit rise in temperature? So, here rho naught is the resistivity at 0 degrees C. Therefore, what is the resistivity at this value and what is the resistivity value at this? So, we express this as fractional change in resistivity at 0 degrees C per unit rise in temperature. So, that is how we define alpha value. Per Kelvin is the unit. Now, depending on this alpha value, the resistivity of different materials vary with the temperature. That can be explained like this. We know the formula for resistivity in terms of number of charge carriers and relaxation time. That is the rho value or sigma conductance is given by N E square R by M into tau. So that is the conductivity. Therefore, resistivity is reciprocal of conductivity. Hence, that is equal to M by N E square tau. You know, N is the number of charge carriers per unit volume. Tau is the relaxation time. Now, in the case of good conductors, so what happens? With increasing temperature, since already they have free charge carriers, their number will increase. But what happens? The collisions become more rapid. So, as the collisions increases, collision rate increases, the average time of collision decreases. Since this tau decreases, M and E are constant. Therefore, the value of rho increases. Due to decrease in collision time, the resistivity value increases with increase in temperature for conductors. Therefore, the graph drawn between rho and temperature, that is resistivity and temperature, will be like this for conductors. So, it increases exponentially with the temperature. Though it shows a linear relation, but it will actually practically the resistivity value increases much with the temperature for conductors. In the case of semiconductors or insulators or wire conductors, the graph will be like this. It decreases. So this is rho value, this is temperature value. With increase in temperature, rho decreases. That can be explained like this. They have semiconductors or insulators have almost zero number of charge carriers at low temperatures. So as the temperature increases, the charge carriers are generated. So this number increases. Of course, the relaxation time also decreases for the collisions, but this increase in number of charge carriers dominates the change in the decrease in the relaxation time. Therefore, it has more effect than this. Hence, due to increase in number of charge carriers, rho value decreases in the case of semiconductors or insulators. So, in that way, we can explain how the resistivity of insulators decreases with increase in temperature. That's about the effect of temperature on resistivity of materials. Okay. Next, we will discuss about the electrical energy and electrical power.